Okay, welcome back. So let's go back. I will create a new notebook for each session. So let me just close this one. We want to save the changes before closing. And then we're going to go back here to our home directory and just create a new notebook. This time we want to talk about simulation codes. Simulation codes. And in particular, focus on the LAMMPS molecular dynamics code. So we are going to import pyiron, project object from pyiron, create a new project instance, and then following the very same pattern as we did before, so we can open this project folder. We now create a structure in this project. Then we use ASE, bulk, and we want an aluminium structure, and we want it to be cubic. We repeat the structure using the setRepeat function. SetRepeat repeats the structure itself instead of returning a new object. So here we do 3 repetitions. And then we want to start and do the LAMMPS calculation. For this we create a LAMMPS job object, again using the project to create this object. So we create job, and we specify the job type, so pure job type. And then we use LAMMPS, and then we give it a job name, and in this case the job name should be LAMMPS. Now we say the structure for the structure that we just selected. So we can assign our structure, and we can select the calculation mode. So we can choose from minimization, a molecular dynamics calculation, a static calculation, or a relation grand canonical sampling. Here we stay with the simple part, so let me just do an MD calculation. Again, we use Shift and Tab to get the options. So we want to set the temperature to, let's say, 500 Kelvin. Now we can look at the other ones, ionic steps, 1000. Now we want to have some more ionic steps, so let's say we want to do 10,000, and I guess the rest of the options is fine for us right now. So we execute this, and we can now directly run our job. And it's going to warn us here that there was no potential defined. So LAMMPS is an interatomic potential code, which is using interatomic potential, and they always have the issue they might be fitted to very specific application. So pyiron by default now chose this Mendeleev potential, but if you want to use this result for application, it's really suggested to explicitly select your potential. And we will do this in the following by doing tests of different potentials and basically iterate over a list of potentials. So here this is just a warning to show, okay, pyiron selected a potential for you, but this is really not a recommended set. Good. Doing this, we can again use our 3D animation. So we can animate our structure and look at the structure 3D. And we see, okay, the atoms are vibrating, and due to the periodic boundaries, some of them are flickering from top to bottom. We can then also import our matplotlib again. iPlot, and we can plot, for example, from the job. Maybe look at this in a bit more detail. So we want from the job object. Oh, there's no job. Oh, it's job and P. Job, and then go to the output. One of the output, we will output generic. because generic is the output that is the same for all codes, so that will allow you to switch between different codes by just changing the job type. If you want to use code-specific settings, that's also possible, but then again, the protocol is not that transferable. And we might be interested in the energy code, right? So the total energy. Looking at it here as an area is not so intuitive, so we would prefer to plot it directly. So let me do this here. And then as an x coordinate, I just select the steps. And I can use it in the x label. That's the steps. And the PLT y label. That's total energy. Plot this, and we can see how they're fluctuating. Another way would be to plot the positions or model the rep positions. So let me take a look at the content of our generic output. So that's what we can do here. Look at this, so we want the unwrapped position so that they're not reflected at the periodic boundaries. You can just copy it here, insert it, and then as is for all the different directions and all the different atoms. So we just use a non-permutation and say we only want the x coordinate. We should also update all. Now we can basically see the fluctuations of the different atoms, how they are moving over the different energy steps. Good. For those of you who are familiar with LAMMPS, so maybe we make this a new chapter. We can also look into the more details of the LAMMPS code. So maybe I just show you this here. So we have the input control. Now it's again LMP input control. And this is the typical LAMMPS file. So you see here there are the LAMMPS commands, how we define the environment, the ensemble, and so on. I just want to briefly show this here. You can again override these by just using edge brackets. So I can say I want to change the number of steps again back to 1000. It complained that the calculation is already finished. That's what we already know how to override. We see here it's now 1000 steps, and we can then again run our job, run, and then use the delete existing option true, and then it's going to execute again. We then have 1000 steps. So we can maybe just copy the last plot that we did here, just to confirm that we have 1000 steps now. That's what we see this here. So it's possible to modify the output, the input scripts manually, but then always there's no longer the opportunity to transfer this to another simulation code. In addition, you can also, if you want to go very deep into LAMMPS, you can also always, maybe we show this here, right? So there's a working directory. If you go into this directory, you find the file there. So we can also get the working directory here. You can then decompress this already from the job. Decompress our files. Now we see all the files that were included in this. Now we can then again open those files using the same notation as before. So you can even, if you want to now parse for a quantity that was not parsed by our universal parser, you can access it here and really directly work with the output files, if that's what you want. Right? So that's very specific to LAMMPS or specific to the code, but we really want to make sure that the codes are extendable for the users and they can really use it in the way that they need it for their projects. Good. So we now talked about LAMMPS and the specific input of LAMMPS. I guess the missing parameter are now the interatomic potentials. So let me just create a new job here, and we will create a job template. So let's do here, create job. And now I'm lazy, I will just type this like this, without the argument. I call it TMP. I can now assign my template job to have a structure, and I just use the same structure defined above. Well, we see I didn't tab, I get a name error because st is not defined, then structure, and the error is gone. And let's say I want to do a, maybe I just make, or then let's say we want to do a minimization. Maybe to make it a bit quicker in terms of the calculation, I will also reduce the simulation cell here. So we would go to just a simple cubic structure for all medium. Here we go, just to reduce the number of atoms. And here we jump back to our simulation folder, so that's the project that we just discussed. Good. We can now use this template job and get a list of potentials. These are all the different potentials that support aluminium, and we don't want to use all of them. We can also look at these potentials in like more pandas Dataframe. So let's then view potentials. So template, view potentials. So here you see the settings and where they are coming from. So some of them are coming from NIST, others are coming from OpenKIM. And we would now maybe want to determine what is the best potential, which one is best in reproducing the lattice constant. So we could say we can do list potentials, and just in the interest of time, I would limit this to 3. Right? So we just iterate over 3 potentials. If you're interested, you can do more, but here we just do 3. We do 4 potential in our list of potentials. Maybe to make it a bit more elegant, we just put this in a new variable, t. Oops. And then we can iterate over those. And what we now want is a new job, hot. And this new job is created as a copy of the existing template job. And then we use the copy2 function. In this function, we get a new job, give a new job name. We want new job name, new job name, and this should be LMP underscore plus the potential name, and then we want new database entry to false. Should be false. Now we have our new job. We assign the potential as spot, and then we run our new job. And we made a mistake. Oh yes, we didn't have a comma here, so that's why it wasn't. I will now use all these potentials and do a minimization for each of them. And you see already, okay, it created new folders for this new calculation, always where the folder matches with the job execute. We can also remind ourselves about the job table. That's what we see here. And we can now use this to inspect one of the jobs, right? So let me load one of them. I want to do pure load. And then we just take, copy paste one of the names. Let's take this one. And now we want to think about, okay, what are the quantities that we might be interested in? And we look at the output, and we look at output, particularly of generic. And then from this generic, we might look at the cells. Right, so we see the size of our cell. We're only interested in the first coordinate, and we can already see, okay, this is we want the last of those cells. So here we want the -1. And then we only want the first coordinate. Right, so this is how we see how these cells are changing. So what we can do now is we can iterate over all jobs. So before job in pure iter jobs, we always want to print, or now we will filter because we only want to iterate over those that we did for this. So we do job name. Now we do it differently. Let's say we LMP underscore in job the job name. And now we can say print job the job name. And we also want to print this lattice constant. Right? So that's just to see how different are the different jobs and what is the lattice constant of those jobs. Good. So well, this is already a quick way to generate new jobs by having this kind of for loops, looping over different interatomic potentials. The data aggregation here is not yet so nice, right? So we want to have more advanced ways of aggregating data. And before I do this, I should structure this a little bit more. So here we said we study potentials. Loop over potentials. That's what we do here. And then the aggregation of data. And now we want to talk more about the pyiron table object. Good. So this is actually the case for the pyiron table object. So we can use this to use the project to create a table. We then define a filter function, def filter, which takes a job as an input and then returns true or false if the job matches. So this would be this if part here. And then we can assign different functions for this, right? So we would like to get the lattice constant, which again takes the job as an input, and then we turn here the shells as we did up here. And now we can attach them to the table object. So we say the filter function should be the filter function we defined. And then the add and the lattice constant equal add. And then we maybe want to add some more functions. So there are a lot of predefined functions. Let's say we will get we could get the job name, right? So just so that we have the same as above. And we could run this table object. And this will iterate over all jobs, filter them with the same criteria, and then summarize all the data in the data frame. Right, so we now have our lattice constant, or part. We could create the potential name from this. Already see how we built like a big data project, which is just using the for loop over different LAMMPS calculations, summarize these calculations, and then get the output filtered like this. Maybe a brief word, you can also do run executions in the background using setting the job type. So if we now want to accelerate this here, what we can do is we could say job potential server run mode dot model equal true, and then this would send the job to the background, and then we could add the delete existing here. System dot true, and here we would do like once we look at the job table, and then we would wait for the jobs to be executed. So if I now execute these cells again, so I would again submit 3 calculations, I will see that they are already running. It sent the execution in the background. And while we scroll over this, we see in the job table there's still one collecting and one is only submitted. The waiting for the jobs is over, and then it already gives us the job table. So that's just a quick advancement in job management, so we can also do non-interactive jobs. Still, the main focus of this tutorial should really be how to set up LAMMPS calculations, create a for loop, and then collect all calculations inside a pyiron table. And with this, I'd like to thank you for participating in the second tutorial. We have another exercise for you, and then we see you for the next one.